Okay, so today we're getting into structures, and this is the biggest topic, most important topic in this class. I think it's the most applicable to engineering problems that you'll do in the future. So this is a really important thing we're getting into. Here you go, Cole. All right, so structures, new topic. And I'm hoping to get far enough today that you can do some problems. We'll see what happens. I'm going to teach this topic differently than books usually do, and so I'm going to give you a quick explanation of why it makes a ton of sense to me. So first, structures are, so a structure is a collection of bodies connected by joints in static equilibrium. A collection of bodies, connected by joints. That's not in static equilibrium. Is called a linkage. And as you can imagine, we don't talk about linkages in statics, but in dynamics, we'll talk about that. In the most popular, the most used statics textbooks, structures are divided into two categories. Those are trusses. And the definition of a truss is every member in the truss has only two forces acting on it. And this requirement, it's a mathematical simplification that does cut down the number of equations a lot, but this requirement means that you can't ever treat members with weight, which is a pretty big drawback to a structures method. So the members can't have weight. And then the other category of structures is frames. And with frames, there can't be more than two members at any joint. Okay, so why do they do that? You know, like, what's the benefit of this traditional approach? And that's just that you can cut down the number of variables and the number of equations a lot. So you can cut down the number of variables and the number of equations a lot. And so, like, when these approaches started being taught as, you know, as the basis of statics, calculations were done by hand, and so cutting down the number of variables and number of equations a lot was a big deal. But, you know, that was many decades ago. Now all your calculators, lots of software on the internet, you can use reduced row echelon form. It really doesn't have the same, you know, it's not as helpful as it used to be. There are a few drawbacks to this traditional approach. The first is, in order to get the right answer, you have to classify the structure correctly, and that's not always like months or years after you take this class. My experience is students don't always get that classification right, you know. So you need to, let's say, put your structure in the correct category. So if you treat something as a truss that's not a truss, then things go haywire. Your answers don't make any sense. Second, after you do the classification, there's two totally different approaches for how to solve these things. So you need to remember two different approaches. And third, maybe most importantly, there are a whole bunch of structures that don't fit into either one of these two categories. So many structures don't fit into either category. So instead, I'll give one approach that solves every statically determinate structure, any structure that has a solution. This will do it. The downside is that you can end up with a lot of equations and a lot of variables. But that's what we're going to do because, with calculators and MATLAB and everything, that's just not a big problem anymore. Also, this approach is it lends itself really well to writing a program to do statics, which, I mean, in my experience working, you don't tend to do a lot of hand calculations. You write programs so you don't have dumb mistakes happen and whatever. And this is something you can easily put into an algorithm. So what does it mean to solve a structure? Solving a structure means calculating the external loads acting on each body. Like for example, this is sort of as simple as a structure can be. You have two members like this. Each one's connected to the ground by a pin joint. They're connected to each other by pin joints. And there's a external load of 500 newtons here. What are the loads acting on each one of those two bars? The way I have that drawn there, if we're neglecting the weights of those things, you can solve that as a truss, by the way. So if that external load of 500 newtons is much, much bigger than the weights, then you get a good answer that way. But if that instead of 500 was 50, and the things have a mass of 5 kilograms or something, then you get a terrible answer using a truss simplification here, because you have to neglect those weights, and those weights would be significant. Okay, so I'm going to give sort of a general method, just a 3-step method, and then I'll get into example problems. So here's a general method for solving structures. So first, number every member and letter every joint, just so we can classify stuff. So if we have a structure like this, just assign a number to each one of these. It doesn't matter what they are. That doesn't change the answer or anything. Assign each one of these joints a letter, just so we can refer to them as we go through it. And now, one by one, for each member, write Newton's second law and the moment equation, Rn2L. So you're going to do a rigid body analysis of each one of those members, write out the table and everything. sure to use Newton's third law, which remember says, you know, like FAB is negative FBA. So you're using the smallest possible number of variables. Once you're done with all of those members, write out your system of equations. As an augmented matrix. And solve using RREF. So in this example, this picture that I drew here, what kind of system of equations would we have there? We're doing this as a two-dimensional problem. Every rigid body gives you three equations. And so this is going to be a system of 1, 2, 3 times 3, 9 variables, 9 equations. And that's a pretty simple truss, or a pretty simple structure. So you can imagine the number of variables gets pretty high pretty fast. And if you're doing a three-dimensional problem, then every body gives you 6 equations. So if you have 10 members in 3 dimensions, that's 60 equations, 60 variables. Well, we're not going to do any like that, but that's how quick it blows up, All right, so before I do an example, here's something that's you have to pay attention to. You can get by in simple problems without really understanding this, but this can be confusing with joints with more than 2 members connected. So for example, imagine a structure like this. Okay, and let's say there's some force applied here and some force applied here. So notice that, well, let me letter these. So let's call the joints A, B, C, D, and E, okay? At every one of those joints, there are more than 2 things connected. At B, D, and C, obviously, like you can see that those members are connected. But at A and E also, there are 2 members connected, and then the ground is also connected to it, okay? C has 4, yes, that's right. That's supposed to connect. Those are all like pin joints. So what you need to do in that case is always choose one base member at every joint that other bodies are connected to. Okay. The approach I'm going to use is, since we're numbering all these members anyways, I'll always use, I'll always choose as the base member the lowest numbered member at each joint. That's a totally arbitrary system, but that's just the system I'm going to use. That's you.
If you don't have a system for choosing, like, don't use the lowest number, you run the risk of having more or less joints. Calculations.
I
use a base twice, and one joint doesn't get properly.
Yeah, it's not really. I think the problem isn't that the joints. The risk that you tend to run into is that you double count a lot of. You double count a lot of contact forces, and if you double count a contact force, then your answers are all wrong. So lowest numbered member at each joint. Okay, so let me number these. I'm going to call this 1, 2, 3, 4, 5, 6. Okay. And I'm going to redraw this. So think of this problem as, okay, so for joint A, I'm going to think of 1 as the base member. Yeah.
So it's 2, 1, like 1 bar.
No, that's 2 separate bars connected at C.
Okay, so it's 37.
Yes. Thank you. Let me make, sorry to mess up your notes, but let me make this 6 and 7. All right, so at the joint A, the base member is 1 because it has the lowest number. So I'm going to have 1 be the thing connected to the ground, and 2 is also connected to 1. And I'm going to draw it like they're connected in different places, but when you actually use those coordinates, it's going to be the same coordinates. So it'll be like this and this. Okay? Are you with me on that? It would probably be easier to see if I drew it in, with outlines or whatever, but it's just harder to do. But I think a diagram like this is a nice thing to do for yourself, especially at the beginning, just to be clear on what's going on everywhere. Okay, so at the joint B, what's the lowest numbered member? It's 1 again. So everything's going to be connected to 1 again. So so 4 goes that way from 1. 2 goes this way from 1. Let me, you know what, let me, I'm going to try color coding it. Okay, are you with me on that? At the joint C, what's the lowest numbered member? 2, so everything connects to 2. So here's 2. So this one connects to it. And this one connects to it. And this one connects to it. Anybody, you need to look at that for a second. Is that all making sense? Yes, every line comes out of the smallest number. So you're taking every joint and you're kind of just visually moving them apart and putting everything on the lowest numbered member, okay? At that joint. So each joint is treated separately. So now we're at the joint D. What's the base member at that joint? 4. So everything's going to connect to 4.
And then in the other two would be the negative of that force. Third one. Or no one gets fleeced out during.
Yeah, so we'll worry about that when we start doing the equations for the individual bodies. So there's one. Here's another one. And now we're almost done. At E, the lowest numbered member is 6. And so 6 will connect to whatever that was, 7, I guess. And the roller will connect also to 6. Okay, so how does this work? Like, what's the reason that you have to do this? Notice that what we've done is we've said this, what's this, 3? Member 3 does not touch member 1, 2, 3, 4 anymore, okay? So there's not going to be any force on 3 by 4 or any force on 4 by 3, okay? If we put those in there, there'd be too many variables to solve for, okay? Down here, there's no contact force from this. There's no contact force from the ground acting on member 2, okay? Even though it's part of that joint. But you can see, if you draw it out like this, you can really see how it all fits together. I don't really draw this out for myself anymore, but if you ever get confused, and I'm sure everyone will at times, you know, that's a way to get yourself unconfused. Okay, let's do a problem. Okay, so let's say that, I know it doesn't look like it, but let's say these are both 20 degrees. And let's say that the lengths of each of these are 1 meter. So that means we can calculate whatever we have to about that horizontal member. And let's say that the mass of the horizontal one is 40 kilograms. Mass of the two diagonal ones are 30 kilograms each. And I guess let's, just so you can see it, let's apply a downward force of 200 newtons at that top joint. And we want to solve that structure. So the first thing I'm going to do is label the joints and label the members. I'll call this 1, 2, 3, and A, B, C. The only place where we have that sort of, the only two places where we have that sort of tricky situation where you have to think about a base member at a joint are at A and C. Up here, there's only two members. Although, I guess in a way, really, we have to think about it up here too, because this force is applied at the, it's applied at the pin, at the joint. So we have to decide which of those two members to apply that force to. Okay, so I guess really I'll think about the base member there and just apply that joint to that. If you apply that external force to both of those two, you're double counting something and it's going to mess you up. Okay, so let me do this again. So member 1 is going to be connected to the ground, and member 2 is going to be connected to number 1. This force, this external force, is going to be connected to member 1, and member 3 is going to be connected to member 1. And then the ground is going to be connected to, or the roller, I guess, is going to be connected to member 2 at C. Okay, so now I'm just going to go through the members one by one. So free body diagram of member 1. So what's acting on it? It's connected to a pin joint with the ground. So there's a force here that I guess I'll call RA. And there's also a pin joint connecting it to member 2. So I'll call that the force on 1 by 2. There, let me move this over. And so I'll write this as RA plus the force on 1 by 2. Okay. And then there's the weight force acting at the middle. So that's 30 times 9.81, so 294.3. And then up at the top, it's being acted on by member 3. So that's the force on 1 by 3. And then there's the downward force of 200. So now we can write out the table. I guess I'll put the about point down here. So the first force, RA, has a row vector of 0. The force is RAX, RAY. Cross product is 0. Then F12, row vector is 0. Force is F12X, F12Y. Cross product is 0. Then there's the mass, or the weight, mg. So the row vector there, this whole thing has a length of 1. So the distance to get to the midpoint is half. So it's 0.5 times cosine and sine of 20 degrees. So that is, what's half of 0.94? 0.47. And then 0.171, I think. And the force vector is 0, negative 294.3. I should have brought a calculator, but can someone multiply 0.470 and negative 294.3? Yes, that is, so the vector, the row vector is this. It has a length of 0.5 because we know the length of the whole member is 1. And if this is the coordinate system, this angle is 20 degrees. And so it's 0.5 times cosine and sine of 20, which is 0.94 and 0.342. Okay. And then we have the force on 1 by 3. That's 1 times cosine and sine of 20. So that's 0.940, 0.342. The force vector is F13X, F13Y. And so the cross product is 0.940 F13Y minus 0.342 F13X. And then we're almost done. One more to go. the 200 Newton force has the same row vector, 0.940, 0.342. The weight force is 0, negative 200. And so that is negative 188, right? 188. Okay, so there's the complete table for member 1. The good news, that's already like a pretty involved, but the good news is that the lower numbered members, if you're using this approach where your base member is the lowest numbered member at a joint, then your lower number members are always going to have a lot more forces acting on them than the higher numbered members. So 1 is always going to be often going to be the messiest looking one. So our equations, let's just write out our equations. So we have RAX plus F12X plus F13X is equal to 0. And then our Y Newton's second law equation says RAY plus F12Y plus F13Y is equal to, add up the two given, numeric loads, and it's equal to 494.3. And then the moment equation says, I guess I'll rearrange those to put the X in front, but negative 0.342 times F13X plus 0.940 times F13Y is equal to, what's 188 plus 138.32? Is equal to 326.32. Okay, so when we were doing rigid body statics, that's one rigid body. We would have 3 variables and 3 equations, and we could solve it. We have 3 equations, but we have a lot more variables than that. Let's think about what variables we have. So we have a full vector of RA, a full vector of F12, and a full vector of F13. So we have 3 equations and 6 variables. So there's nothing we can do yet. We just have to set these equations aside, know where to get them later, and these equations are going to go into our big augmented matrix. Okay? So now let's go to member 2. So this is the horizontal one. On the left side, what forces are acting on member 2? Let's look at this little colored sketch I did. There's one, it's connected to member 1, but just not the reaction from the ground. Okay? So over here, there's a force on 2 by 1, which, since we've already used F12, we'd rather write this as negative F12. You with me on that? And then what about on the right side, what's acting on it? Number 3 is acting on it, and that roller is acting on it. So we have a force on 2 by 3, and then we have the force that's produced by the roller. That's going to be perpendicular to the surface toward the chosen body. So this way, I'll call that RC. And then don't forget the weight. So this is 382.4. Don't. I'm going to use this as my about point. All right, so the first force is negative F12. The row vector is 0. The force is negative F12x, negative F12y. Cross product is 0. The second one is the weight. And now we have to figure out how long that piece is. So I guess it's going to be 2 times the cosine of 20. So what's that, 1.88? Okay, and so halfway there is 0.94. The weight is 0, negative 392.4. What's 0.94 times negative 392.4? Okay. And then F23. Let me just finish this second body. I can't finish this whole problem, but I'll finish this second body, and then I'll finish this up and put it on D2L, and you can see what I do. So the row vector is 1.88, 0. Force vector is F23x, F23y. And the cross product is 1.88 F23y. And then the last one is RC. That has the same row vector, 1.88, 0. Force vector is 0 RC. Cross product is 1.88 RC. We already have 3 equations, so now we're going on to equations 4, 5, and 6. The X equation from Newton's second law says negative F12x plus F23x is equal to 0. Equation 5 says negative f12y plus f23y plus RC is equal to positive 392.4. And then equation 6 says 1.88 f23y plus 1.88 RC is equal to 368.86. Okay, 2 more minutes. 1 more minute. So now we have 6 equations. We only had 6 variables after the last body, but what did we have now? Did we add any? We also added, so we still have the ones we had before, F12, F13, yep, and we added F23 and RC. So now we have, is that, oh, and I'm missing RA. RA and RC. So now we have 9 variables and only 6 equations. So we still can't solve for anything yet. And so, but we still have these 6 equations that are going to go in our big matrix at the end. Okay. And what you'll see is when we do the next body, the last body, we're not going to have to add any more variables. We'll have 9 equations and 9 variables. We can plug it all into the matrix and solve for all of those. Yep.
Would you recommend bringing a laptop in as we do this, so we can, if we're going to be doing those big matrices?
No, I don't think so. Really.
Like I can't.
Yeah.
It's hard for me to follow along trying to read. Would it be bothersome?
It wouldn't be bothersome. I don't know if you would find it made it any faster, but we're not going to be doing a lot of this. I mean, but I mean, you could try it, see if it works, see if you like it better. Okay, let me pause this. All right, so now we're on to the last member, member 3. And if we go back up to this, the only members touching it are member 1 up at the top and member 2 down at the bottom. So up here, we have negative force on 1/3. Down here, we have negative force on 2/3 because we've already used the forces F13 and F23. And then we have the weight of 294.3. I'm going to choose this as the about point. So first, the force negative F23, the row vector is 0. The force is negative F23x, negative F23y, 0. And then the weight, that's going to be, negative 1/2 times cosine of 20, positive 1/2 cosine of 20 is the row vector. So negative 0.470, positive 0.171. The weight force is 0, negative 294.3. And the cross product is positive 138.32. And then the last force is negative F13. The rho vector is 1 times, you could think of it as cosine and sine of 160, or negative 1 times cosine of 20, positive 1 times cosine of 20. So the rho vector is negative 0.940, positive 0.342. Force vector is negative F13x, negative F13y. Cross product is 0.940 F13y plus 0.342 F13x. We've done 6 equations so far, so now we have equations 7, 8, and 9. Negative F23x minus F13x is equal to 0. Equation 8 says negative F23y minus F13y is equal to positive 294.3. And then the moment equation, the last equation, says 0.342 times F13x plus 0.940 times F13y is equal to negative 138.32. And now I am going to snap my fingers and produce an augmented matrix. Okay, snap, and let's see, capture. There it is, that's the augmented matrix. And then if you do reduced row echelon form, you get F12 vector is equal to 679.3, negative 196.2. F13 vector is equal to negative 679.3, positive 100. The F23 vector is 679.3, negative 394.3. The reaction at A is all vertical, 0 for X, 590.5 for Y, and the force at the roller, RC, is 590.5 newtons, which is a good sign because that roller can't produce, can't pull, so it needs to come out positive. And so now if you were trying to figure out how worried you are about these individual members breaking, now you would plug these values back into your original free body diagrams of the members, add up any forces that are acting at the same point, and it would give you the total external loads acting on each one of those members. Okay, so it looks complicated at first, but once you get used to this system, this is one single approach will work for any kind of structure problem you ever deal with.